Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. One of the biggest puzzles in science today is something so fundamental. It almost sounds philosophical. Is gravity a quantum thing? We have an incredibly successful theory for the quantum world. That's all the tiny particles and forces except gravity. And we have Einstein's great theory for gravity on big scales. But these two frameworks don't fit together. They're like pieces from different puzzles. Now, imagine trying to build an experiment that could show whether gravity itself has a quantum side. That's like trying to catch a ghost with a butterfly net. It's really hard. But physicists are celebrating a new breakthrough. They've managed to use lasers to cool a device, a human-scale mechanical object, to an extremely quiet, cold state, hoping to reveal gravity's quantum whispers. It's a mouthful, but let's break down why laser cooling a heavy object could inch us closer to a theory of everything. Setting the stage, why we care. If gravity is quantum, all the other fundamental forces, electromagnetism and the weak and strong nuclear forces, have been successfully described by quantum theory. This means at a fundamental level, those forces come in little packets or particles, like photons for electromagnetism. But gravity? We don't have a proven quantum theory for it. Einstein's general relativity describes gravity as the smooth bending of space-time, beautiful for planets and galaxies, but it doesn't play nice with quantum physics at tiny scales or high energies. Physicists have proposed all sorts of ideas, strings, loops, maybe a particle called the graviton, to quantize gravity. But no one knows what's right because we haven't been able to test gravity in the quantum regime to really find out if gravity obeys the weird rules of quantum mechanics, like superposition and entanglement. We need an experiment that involves gravity and quantum effects together. The trouble is, quantum experiments usually involve very small things, atoms, photons, etc. And gravity is extremely weak on those tiny scales. Conversely, larger objects have noticeable gravity, but are very hard to keep in a delicate quantum state because they interact with the environment and shake around, ruining any quantum behavior. It's a catch-22, big enough to feel gravity's pull, but small and isolated enough to show quantum weirdness. The ingenious approach, laser cooling, a torsional oscillator, entered this new experiment from a MIT-led team. They targeted a device called a torsional oscillator. You can picture it as a small bar or platform, suspended in a way that it can twist back and forth. Kind of like a very sensitive wheel or a hanging paddle that can rotate a tiny bit. Historically, torsion balances were used in classic gravity experiments, like measuring Newton's gravitational constant G back in the 18th century, Cavendish style. They're super sensitive to tiny forces. Now, imagine making one the size of a thumbnail or so, and you want to see if you can get this thing so quiet that it starts behaving quantumly. The team managed to cool a centimeter-scale torsional oscillator down to just 10 millikelvins. That's 0.01 degrees above absolute zero. In other words, extraordinarily cold. At that temperature, almost all the random jiggling from heat is gone. They did this using laser cooling techniques. Usually, we hear about laser cooling for atoms, shining carefully tuned lasers to slow atoms down. Here, they applied it to a mechanical object. They bounced laser light off a tiny mirror attached to the oscillator. As the oscillator moved, the light's reflections provided feedback that saps away energy from the motion, damping it out like an optical break. Achieving this on something visible to the naked eye, centimeter scale, is a first-of-its-kind accomplishment. Why does being this cold help? Because quantum effects only show up clearly when an object's motion is near its lowest energy state. At room temp, even a small object is vibrating like crazy with thermal energy, completely washing out subtle quantum behaviors. At 10 MK, the oscillator's vibrations are minimal. It's nearing the so-called quantum ground state. That means the oscillator is so still and quiet that any remaining motion might be due to tiny quantum fluctuations rather than jostling from heat. This sets the stage to test gravity's effect on it. What's next? Using the setup to probe gravity's quantum nature. Cooling the oscillator is a milestone. It's not the end goal by itself. The idea is now, you have this ultra-quiet, isolated little torsion pendulum. The dream experiment would be to put it into a quantum superposition, like having it in two twist states at once, or to entangle its motion with another system, and then see how gravity behaves. For example, one proposal people talk about: take two tiny masses, put them each in a superposition of two locations, and see if their gravity can entangle them. If you observed gravitational entanglement, that would strongly hint gravity is quantum, because entanglement is a quantum phenomenon. Those kind of experiments are unimaginably delicate, but the work done here is a stepping stone toward them. By having a mechanical oscillator that's almost quantum, they could, for instance, test whether gravity causes decoherence, i.e., forces a quantum system to go classical. But even without full-on entanglement tests, this apparatus can help measure subtle effects. It can act like a bridge between the quantum and gravitational realms. Maybe they'll measure tiny vibrations induced by gravitational forces at the quantum limit, or test inverse square law at microscopic scales, etc., all with unprecedented precision. Historically, torsion balances discovered fundamental things, like the existence of gravitational constant or testing equivalence principle. A quantum-capable torsion balance might discover new subtleties in gravity. Does it have an unexpected behavior at very small scales? Does it produce little random kicks, maybe due to hypothetical gravitons? And beyond gravity, this innovation could improve technologies like quantum sensors and clocks. But sticking to the big question, every step like this, making a larger and larger object behave quantum mechanically, is a triumph in itself. We started cooling individual atoms decades ago. Then tiny nanomechanical resonators, now something on the centimeter scale. It's like the quantum world is steadily scaling up in our labs. Gravity is also quantum. At some point we'll catch it acting funky, like showing interference or entanglement. If we never see that, and gravity always acts classically, even on quantum objects, that's equally huge news. It might mean new physics is needed. Closing thought. This achievement is a bit like designing a super quiet room to eavesdrop on a whisper from nature. We haven't heard the quantum gravity whisper yet, but we've at least hushed the other noise enough that we might, just might, detect something. It's a profound moment. We're engineering devices at the edge of what's technically possible, all to answer a question about the fundamental workings of reality. Will gravity join the quantum club? Or will it remain the odd one out? Thanks to innovations like laser-cooled torsion oscillators, we're closer than ever to finding out. It's a beautiful example of human curiosity, building extreme experiments to coax secrets from the universe. And it leaves us wondering, if and when we finally get evidence of gravity's quantum nature, how will that revolutionize our understanding of everything from black holes to the birth of the universe? The quest continues, quieter and cooler than ever.